Hello guys, so in today's video we are going to look at RSA algorithm, and in particularly we are interested in CRT optimization of RSA algorithm. Okay, so let me first explain what do I mean by this, and then we will look at the solution for it. So in general, if you see RSA, so the RSA algorithm is basically we begin with two prime numbers p and q. Then we compute something known as n, which is equals to p into q. This is modulus. Then we compute something known as Euler's Torsion function, which is phi n, which is equals to p minus 1 into q minus 1. Then we assume an e, which is known as public exponent, and then this e should be an odd number, and it should be less than phi n and greater than 2. Okay. So once we have this public exponent, e is known as public exponent, we compute something known as d, which is private exponent. And to compute private exponent, the condition is ed is congruent to 1 mod phi n. So we will get our private exponent, and then once we have all these components, then we can perform encryption. So basically, let us say there is a plain text and we want to perform encryption. So basically, from plain text we will get our ciphertext. So then the ciphertext will be equals to plain text to the power public exponent modulo n, and so this will give us our ciphertext. And once we have ciphertext, if we want to convert it to plain text, which means we want to perform decryption, then plain text is equals to d, which is private exponent modulo n. So this is what the RSA algorithm is. Now within this, this is okay. This is not a costly operation, not a costly operation. And here by costly, it simply means time wise. In order to perform or in order to compute the ciphertext, uh, we don't require a lot of time. The reason for this is that in practice we generally use public exponent as 65537, and then plain text to the power 65537 is something which can be computed relatively faster. Usually what happens is that when we compute d using this, when we compute d, then d tends to be a very large value. D is a very large value. Okay. Now since d is a very large value, then ciphertext to the power d, this computation will take a very lot of time, right? So here the time wise, it will become a very costly operation. CT to the power ciphertext to the power d will become a very costly operation. And this is what is, and this problem or this is there a way by which we can optimize this CT to the power d? Can we optimize this? Is something which can be done using Chinese remainder theorem, which is known as CRT. So RSA with CRT will help you in optimizing the computation of CT to the power d. Okay, in practice, if you want to do CT to the power d, then naturally it is going to take a lot of time, but with help of Chinese remainder theorem we can do it much efficiently. So now let us look at how can we perform CT to the power d efficiently, or how can we optimize it. Okay, so for this let us take an example. Let us assume that p is 7, okay, q equals to 11. Since p and q are this, so n, which is equals to p into q, is equals to 7 into 11, so n equals to 77. Okay, this is 11. And let us choose an e which satisfy the properties e should have. So let us say e is equals to 13. Okay, and just for completeness, phi n is what? P minus 1 into, so 6 into 10, q minus 1, so this will be 60. and E is less than 13 is less than 16, it is greater than 2. So E is correct. Now the thing is, what should be the value of D? Well, D can be computed using extended Euclidean algorithm, and by applying extended Euclidean algorithm, if you solve this entire thing, then E will come as D will come as 47. Okay. By the way, I have made a detailed video of RSA and how can we perform extended Euclidean algorithm also. So there are two videos on my channel which deals with RSA, and the other video is for extended Euclidean algorithm. If you want to know how exactly this 47 has come into picture, you can refer to those videos and you will get a way how we can apply extended Euclidean algorithm to deduce the value of D. Okay, but for this video we are going to say that by applying extended Euclidean algorithm we got the value of D as 47. Okay, so okay, so that is okay. Now let us perform encryption, and let us say our plain text is 15. Okay, now with this let us first do encryption. Okay, so we want to perform encryption. So as we know, encryption is basically we will get ciphertext. So ciphertext is equals to plain text to the power E modulo n, right? So let us compute it. So this is basically equals to plain text. What is the plain text? Which is 15. E is what? E is 13 modulo n. N is 77. So if you compute this 15 to the power 13 modulo 77, you will get ciphertext as 64. Okay, I'm skipping the computation, but if you want to compute it, you can compute it on your own and you will see that the ciphertext is 64. Okay, all right, so ciphertext is 64. Now let us look at decryption, and essentially in the decryption case is where our CRT will come into picture. Okay, so let us look at decryption. So if you want to perform decryption, and in the plain in simpler terms, plain text will be equals to CT to the power T mod n, right? So now let us plug the values. So ciphertext is what? 64, and D is what? 47, right? And mod, this is 77, right? And this is what I was talking about, that this exponentiation is a costly operation. This is the costly operation we have, right? And using CRT or Chinese remainder theorem, we will be able to optimize this. So using CRT, in a way, we don't really have to compute 64 to the power 47. Uh, we have to compute some exponentiation, but it won't be this big. Okay, now let us see how CRT help us in optimizing this. Okay, so let us look at CRT now. Okay, so we know that in order to get plain text, we have to perform ciphertext to the power D mod n, right? And n is what? P into Q. So we can write it as CT equal plain text equals to ciphertext to the power D modulo P and Q. P into Q, sorry. P into Q, right? And we also know that P and Q are prime numbers, so GCD of P and Q will be 1. Since the GCD of P and Q is 1, okay, since they are prime numbers, because of which we can say that plain text is equals to, we can break it down as plain text equals to MP Q into Q P minus 1, okay, mod n plus MQ P to the power Q minus 1 mod n, and this entire thing is modulo n. Okay, so this is in multiplication modulo n. So this is what, using Chinese remainder theorem, we can optimize pt equals to this part. Okay, now clearly here, for instance, let me use a different ink here. So here we had to compute this ct to the power d, whereas here we don't really have to compute that kind of ct to the power d. This is what we have to worry about. This is what we have to worry about. And the thing is that p and q are already known to us. So q to the power p minus 1 is something which will be constant for most of the cases, and we can pre-compute it and keep it with us, and we can use it while we are implementing RSA algorithm. Okay, but here, as you can see, there are two terms which we have not talked about, which is MP and MQ, right? So one may think, what is MP and what is MQ? Okay, so let us look at what are the values of MP and MQ. Okay, so basically MP is equals to ciphertext to the power a D modulo P. Okay, now here again, we may think that again we end up computing ct to the power d, but that is not the case. What happens here is that we can say that d, and let us say we are dividing d by 5p. Okay, we are dividing d by 5p, and 5p, since p is a prime number, so 5p becomes p minus 1, right? So this becomes d becomes p minus 1 into some x, right, plus d mod p minus 1, right? So basically what I am doing here is that there is d, I am dividing it using p minus 1. So it goes x times, and then there is something here, and then we got some remainder here, right? So this is a remainder, right? So this equation, right, this equation is basically p minus 1 into x. So this into this plus remainder. The remainder is what? D modulo p minus 1. Okay, so I hope that is clear. So this is how we are writing d as. Now let us plug the value of d over here. So what we will get is that MP is equals to ciphertext to the power p minus 1 into x plus d mod p minus 1. Okay, and this entire thing is mod p minus 1, right? Now we can rewrite MP as, so MP will be ciphertext ct to the power p minus 1 times x, okay, modulo p minus 1. Okay, so and this equals to ct to the power d mod p minus 1, okay, and modulo p minus 1. Okay, and then this entire thing is modulo p minus 1. All right, now what happens is that using Fermat's little theorem, okay, using Fermat's little theorem, this term will evaluate to 1 mod p minus 1, and that is why we basically have distributed d in terms of 5p. Okay, so this becomes 1, so because of which now MP get reduced to, or MP has been optimized to, MP will become ciphertext to the power dt, which is d mod p minus 1, okay, modulo p minus 1. Okay, So MP get reduced to this. All right. So we see this now, like earlier we had to compute Ct to the power d. Now we just have to compute Ct to the power d mod p minus 1. So this is what the optimization is. Okay. Now similarly, MQ, if you do the same kind of operation with MQ, you will get MQ as Ct to the power d mod q minus 1 modulo q minus 1. Okay, so MP and MQ are this. All right. Okay, so MP and MQ are this, and this was our equation. Okay, so now let us use this and try to get our decryption key. Sorry, try to get our plain text. So we know that plain text is equals to MP into Q to the power P minus 1 modulo N plus MQ. So this is what we have to compute. So first we will go ahead and compute MP and MQ. Okay, so let us compute MP and MQ. So let me just compute MP. So MP is equals to what? Ciphertext. Ciphertext is 64 and D mod P minus 1. So D is what? D is 47 modulo P minus 1, right? So P was, let me write it down here. Okay, or let me use a different page. Okay, and let me just rewrite the things which we have seen. So what was the value of P? P was 7, Q was 11, E was 13, N was 77, phi N is what? 60, right? And D is 47. And we started with plain text which is equals to 15. We computed ciphertext which was equals to 64. Now we wanted to compute MP. So let us compute MP. MP is equals to what? CT ciphertext to the power D mod P minus 1 modulo P minus 1, right? I'm so sorry. Oh, okay. I am so sorry. This is just P, mod P. Okay. I'm sorry. Let me just correct it. So sorry. This is, yes, MP equals to mod P. And so let me just correct it. MP equals to, this is mod P, not mod P minus 1. This is mod P. And yes, and this is ciphertext to the power. This is mod P. This is also mod P. And this is also mod P. This is not the case. And MP is equals to, everything is correct here. This is mod P and this is mod Q. Okay, so mod P and mod Q, not mod P minus 1 or Q minus 1. Okay, so MP is this. Now let us plug the values. So MP will be equals to, ciphertext is what? 64, right? And the value of D is what? 47 modulo, and let's do P minus 1 here. So P minus 1 is what? 6. Okay, and this is what? Mod 7, right? So this becomes MP is equals to 64, and 47 modulo 5 is what? 5, right? 5 is the remainder there, and this becomes mod 7, right? So now here clearly MP is 1, right? Is 1 modulo P, 1 modulo 7, right? If you divide 64 by 7, then 1 will be the remainder and 1 to the power 5 is 1. So essentially MP is 1. Okay, and now let us look at MQ. Okay, so MQ, now we know that MQ will be equals to ciphertext to the power D mod Q minus 1 mod Q. right? So now that simply means MQ equals to what? Ciphertext is 64, 47 modulo Q is 11, so modulo 10. Sorry for this, modulo 10, and this is modulo 11. Okay, so MQ is equals to 47, and the remainder here is 7. I'm so sorry, this is 64. 64 to the power 7 modulo 11. Okay, and if you solve this, you'll get MQ as let me see what was MQ. Okay, MQ, you'll get MQ as 4. Okay, so if you solve this, which is like 64 to the power 7 modulo 11, you'll get MQ as 4. Okay, now let us plug this value in our original equation. So our original equation was what? Plain text equals to MP Q to the power. So let me write it down here. So our equation was plain text is equals to MP into Q to the power P minus 1 modulo n plus MQ P to the power Q minus 1 modulo n, and then this entire term is modulo n. Okay, so we know that MP is, or we have computed the value of MP and MQ. MP is 1 and MQ is 4. Now let us compute the value of Q to the power. So let us compute the value of these two terms now. These two terms, which is this and this, let us compute it. So let us compute Q to the power P minus 1 modulo n. So this is basically equals to Q is what? 11 to the power 6 modulo 77. So if you compute this, this is basically equals to 22. Okay, similarly P to the power Q minus 1 modulo n, if you compute the other term, so P is what? 7 to the power 10 modulo 11. Okay, this is 11, and if you compute this, you'll get this as 56. Okay, so once we have computed all the terms, so let us plug the values into this equation. So now plain text becomes equals to 22 into MP, MP is 1, plus 56 times MQ, MQ is what? 4 modulo n, n is what? 77. So from here what we will get as plain text equals to, so if you solve this entire thing, you'll get plain text equals to 15. Okay, so this is how, using CRT optimization, you will be able to solve RSA algorithm, or you can optimize the decryption portion of the RSA algorithm. So I hope the video helps, guys. In case if you have any questions and queries, please feel free to drop it in a comment and I'll try to address them. That's about from this video, folks. Thank you.